Hey everybody. Today I wanted to introduce you to planes. And what I mean by that is not an airplane, but a surface, right? And a surface that we've been working with on a flat surface, right? The XY plane, for instance. But in this unit, we're going to start talking about, well, how do we orient it at an angle? Or how do we move it here instead of here? And so that's what a plane is. So let me make myself a little bit smaller and off to the edge here. And we're going to talk about what a plane is. And so I'm going to bring up an example. I have a little app here that'll allow us to look at a bunch of different planes. And so you can see in 3 dimensions here that surface going all over the place. So that is a plane. So a plane is a flat surface that has no thickness, no edges. And the standard form for a plane is any equation that is of the shape something x plus something y plus something z equals something. And so when we do that, first trio, A, B, and C, that is a vector that is perpendicular to the plane. And you can see that here. We call that vector the normal vector. Kind of a strange name, but that's what it is. That's it. Any vector that's perpendicular to a plane is called a normal. And then because of this equation, any x, y, and z, any combination of numbers that makes this equation true is going to be a point that's on the line. So if I can summarize what we're going to be talking about for the rest of the day in kind of one thing, you'll need to realize that the orientation is determined by A, B, and C. That's the normal vector. And then where the plane is, its location, is determined by this number D. So I'll try to show you that in a couple different examples with GeoGebra a moment. So as I rotate this around and so forth, I'm going to just tweak these numbers a little bit. So you'll notice that as I tweak those, the orientation of the normal vector and therefore the plane changes. So if I want to rotate it around a little bit, I can change A or B or C. And then if I'm happy with the orientation of the plane, but I want to move it up or down or in or out, away from the origin or closer to the origin, then I adjust D. So that's how you can control where a plane is and how it's oriented. So a couple of questions. First question, is the point 3, 5, negative 7 on the plane 2x plus y minus 5z equals 50? And so to answer that question, what you need to do is plug in the point 3 and 5 and negative 7 in for x, y, and z, and then we can calculate this. And if it comes out true, then the point is on the plane. If it comes out false, it's not. So let's see here. 2 times 3 is 6. 6 plus 5, let's see, this turns out to be a plus 35. And so 6 and 5 is 11, plus 35 more is 46. 46 is not 50, although it's close. And so what that means is that the point 3, 5, negative 7, while it's not on the plane, is relatively close. So let's see that a moment. Let's make our plane be 2x and 1y and minus 5z and set that equal to 50. And so here's where that plane is. And let's plot the point 3, 5, negative 7. And you'll see that that point is really close to the plane, but not quite on it. So, next question. Write an equation for a plane that's parallel to this one, but goes through a specific point, 1, 10, 5. So let me start with that plane, x plus y minus 3z equals 10. And if I want this new plane to be parallel to that, then I want to keep the orientation the same. So I don't want to change the number in front of x or y or z, But what I do want to change is this number over here. And so how do I decide what that number needs to be? Well, I'm going to plug in the point 1, 10, 5 in for x and y and z and see what it calculates out to. So let's do that. 1 plus 10 minus 3 times 5. That would be 1 plus 10 is 11 minus 15. So 11 minus 15 should be a negative 4. And so what I need then is this to be a negative 4. And that should do it. Let's check that a second with GeoGebra. So I want my new plane to be, where did it go here? I want it to be parallel to this one, but to go through the point 1, 10, negative 5. So to make that happen, we said we needed the orientation of the plane to be a 1 and a 1 and a negative 3. Oops, there we go. Notice those planes are parallel. And to get it to go through point Q over there, which is 1, 10, 5, I needed to have the orientation be, or the D value be a different number. And so we said that needed to be negative 4, and that looks about right. So what's next? We need to find a point that's on the plane x plus 2y minus z equals 10. Now, there are millions of points. In fact, there's an infinite number of x, y, z combinations that would make this true. And so we simply need to find some combination of x and y and z that make, not this equation, oops, that make this work out. For instance, if x is a 10 and y and z are both zeros, that would work. So let's maybe make a list of some of these points. 10 for x, 0 for y, 0 for z. That would be a point that would work. If y was a 5 and the other two things were zeros, that could work. If x was a 12 and z was a 2 and y was nothing, that should be a combination that works, right? 12 plus nothing minus 2, that equals 10. And you could see how we could play this game forever, and we will find more and more and more points that are on this particular plane. Now, two of these points, 10, 0, 0, and 0, 5, 0, are special points. And so planes, like lines, have intercepts. So a plane has an x-intercept and a y-intercept and a z-intercept. And I should say usually. Sometimes the planes might be parallel to the x-axis or the y-axis and they might never intersect. But most planes will have x, y, and z intercepts. And their coordinates are when two of the three variables are zeros and you have something else for x or for y or z. So I want to show you those intercepts a moment. So let's turn on the intercepts, turn off some of these extra things. So you can see, let me adjust these numbers a little bit. So here's a plane, and you can see that that plane intersects the x-axis, and the y-axis, and the z-axis at 3 points. Those are called intercepts. Most planes also have what we call traces. A trace is where the plane might intersect the xy plane, or the xz plane, or the yz plane. Those are going to be lines. So I'll show you those in GeoGebra in a moment. So I'll turn off these x, y, z intercepts and turn on these traces. So you can see that that plane intersects the xy plane at this line called the xy trace, and so on. Those are unique things. And if you're going to draw a plane, which is really hard to do in 2 dimensions on a paper, but if you have to draw a plane, it's sometimes helpful to plot the x, y, z intercepts or to plot the x and y traces. Sometimes it makes it pop out a little bit. So what sort of questions can we answer with this? So here, find the intercepts of the plane 2x minus 4y plus 8z equals 40. So if we want to find the intercepts, we need to remember that those are the special points where 2 out of the 3 coordinates are 0. And so if we want to find the x-intercept, that's going to be the point where y and z are 0. And so we can use what's sometimes thought of as the cover-up method, perhaps. If we want to cover up y and z, because y and z are 0, I know you can still see them, but imagine they're not there, then we have the equation 2x equals 40. You can divide both sides by 2, and we get that x has to be 20. And so what that means is the point 20, 0, 0 is not only on the plane, but it's a really important point. It's the x-intercept. If we wanted to figure out the y-intercept, then x is a 0 and z is a 0. And we need to figure out what would y have to be to make things work. So if this wasn't here and this wasn't here, oops, one too many of those. So there was no z and there was no x. There was just negative 4y equals 40. Then we would divide both sides and we would get what y has to be a negative 10. And finally, if we wanted to find the z-intercept, then x and y are both zeros. And if we divide those out, we get that z would have to be a 5. So those 3 points are some points that are on the plane. And again, they're kind of some important ones. If you were going to try to draw this plane, those would be some points that you'd want to put on your x and y and z axis. One last question for today. Write an equation for a plane if it has these particular intercepts. Now, I will tell you that there's lots of correct answers for this question, and so we're going to find the equation that has a d value of 42, and I'll show you how you can tweak that to make any of the other answers if you want. So, to make that happen, let's pull out a general formula. Something x plus something y plus something z equals something. And what we know is that if we plug in a 3 for x and a 0 for y and a 0 for z, we know that this equation needs to come out true because this is a point that's on there. And so if there was no, if x is 0, then 0 times b is gone and 0 times c is gone. And so we need to come up with an a and a d combination that makes this work, makes this true. And I told you this is why there's lots of right answers, because you could pick any a and d so long as 3 times a is that number over there. And I said, let's make d be 42. So I can go up here and we're going to say d is 42. And if d is 42, then, well, in order for 300 to be a point on the plane, a would have to be whatever 42 divided by 3 is. I think that's 14. So let's make that a 14. Likewise, if the point 0, negative 6, 0 is on this plane, then that means if we put a 0 in for x, this term goes away. If we put a 0 in for z, this term goes away. And we have a negative 6 in for y. In order for this to be true, b would have to be, is it negative 7? I think so. So we'll make that minus 7. And finally, if we want to figure out what number goes in front of z, then we need to put a 0 in for x and a 0 in for y and a 7 in for z and see what we get. I'll get rid of these guys because those are zeros. And I'd have to divide both sides by 7. And so c would have to be a 6. So this is one of many different equations that would have an x-intercept of 3, a y-intercept of negative 6, and a z-intercept of 007, James Bond. If you wanted to come up with another one, you could take everything in this equation and scale it by some number. You could multiply everything by 2, for instance. And this equation 28x minus 14y plus 12z equals 84. That would be the exact same plane. It'd be the same graph. If you wanted to, you could take everything in these and maybe scale it by dividing everything by 10. So 1.4x minus 0.7y plus 0.6z equals 4.2. That would be another equation for the same plane. So I'm not going to get into which equation is best. I'm not even sure there is a which equation is best. But just realize there are more than one way to write the same equation for a plane. Might as well check this real quick. So let me hop on GeoGebra, and we'll make our A 14 and our B -7, our C a 6, and our D a 42. And let me turn back on the X, Y, and Z intercepts and turn off the traces here. And so it's a little hard to see here, but if we zoom in on just that x-intercept looks like it's at 3, about halfway to 5 there. The y-intercept is definitely backwards on the y-axis, the green axis there. And I think it's not too hard to think that that's that far out. And the z-axis definitely looks like, or z-intercept here definitely looks like it's at a 7. And so I think we got it. Anyway, there is a brief introduction to planes. Thanks for watching. Tune back next time to see how we can use the cross product to help us define planes.